Well, okay, so I'm going to go ahead and, since it's being recorded, I'll go ahead and start doing Dr. McCohen's material. So you all recall the Taylor polynomials. From one variable calculus. So if you center a function at A, then you can have a Taylor polynomial of the form what the function is at A and the derivative of function at A times h, and then there's this 1/2 second derivative h squared and so on. Okay. So the general formula was that if you take the nth derivative of the function evaluated at A times h and you divide by n factorial, and you sum as n goes from 0 to infinity. So the first two terms here are the linear approximation to the function near A. The first three terms are the quadratic approximation. So, and when dealing with the linear approximation, the third term was important because it allowed us to prove that the second derivative test, right? So the idea is that we need to develop some theory for a function of many variables that's similar to this one. Okay. So for a function of many variables, you would still have the function at A and the derivative of the function at A times h, so that's the linear approximation. And then you would have a quadratic form. So that would be in the form h transpose times the second derivative matrix, which we're going to call a Hessian. Okay. And then you're going to have higher order terms, and those can be combined into a remainder defined at A acting on h. And the property of the remainder is that if you take its norm and divide by even a magnitude of h squared, this is going to go to 0 as h goes to 0. Okay. And we really want to develop theory about this second order term here. Oops. The second order term, because it's the one that's going to provide this the theory for the second derivative test. Okay. So what do we know about the Hessian? Well, it's a matrix of second order partial derivatives. Okay. So if we would have, so these are for functions from some subset of Rn into Rn. So it's just the derivative, the mixed partial derivatives. I guess I could call it squared. So I'm not going to write it down, but it's the matrix of second order derivatives. Now, what would it take for this matrix to be symmetric? Well, the component functions of f have to be C2, so you could use Clairaut's theorem to show that mixed partials are equal. Right, so these have some kth component, and then you differentiate with respect to xi and xj. That should be the same. And in that case, your matrix is symmetric. And for the one variable case, we proved the second derivative test by saying, well, if the second derivative is positive at a critical point, then we know that the function contains a minimum, and if the second derivative is negative, then we know the function contains a local maximum at a critical point. Right? So the idea was for a function from R to R, if you have A as a critical point, then a necessary condition is that the derivative is 0, assuming your function is smooth, right? So differential. Okay, so if you look at your Taylor polynomial, and then you have the remainder. Then this became because we had a critical point, this became 0. And so, oops, f of a plus h, sorry, should erase that. And the idea is that if this derivative is positive, this is obviously positive, then this would be less than or equal to f at a, right? So if you take any point close to a, then that's going to be less than or equal to what the function is at a, and then we can take care of the, I guess, the remainder later on. So you had a, so you know that you had f at a as a minimum. And similarly, if this was negative, this is positive, then this whole thing was negative, so that would be bigger than, so f of a would be bigger than f at a plus h. Okay, so that means, what does that mean? I think I get that backwards. Sorry. Right, so if second derivative was negative, then you had a local max instead. So instead of looking at the function of one variable where the second derivative is either positive or negative, possibly 0 or when the second derivative test failed, we have to look at this Hessian, the symmetric matrix. Okay. And so, for example, it might be, let's see. So for a function of two variables, say, here you would have h as the displacement from the point AB, and then you would have your second derivative. And this is your Hessian of the function at A. AB, I guess. and plus some remainder term. Yeah, okay, and then h, whatever. And so we need to, if AB is a critical point, then it's easy enough to see that the derivative, it's a necessary condition that the derivative of f at that critical point is 0. Okay. And instead of asking whether this Hessian matrix is positive or negative, we ask whether the Hessian matrix is positive, definite or negative definite. So this notion of positive definite negative definite or neither is like, for one variable calculus, is like asking whether the second derivative is positive or negative, except we're dealing with matrices. Okay. So what is a positive definite matrix? Kind of your understanding of it. Ooh, it's not good enough that the determinant is positive. So we'll start with the definition of positive definite. So we have, let's call it S, a matrix, it's an n by n matrix, and it's symmetric. Then if you have V transpose times S times V, or maybe you see this written as V dotted with S times V, if you will. If that's always positive for all non-zero vectors, then we say that this is S is a positive definite. Right, so that's going to correspond to our Hessian over here. Right, notice it's in the form some vector times the matrix times a vector. So if that's positive, that's like the second derivative being positive. Okay. And what were some equivalent conditions for a matrix to be positive definite? Well, all the eigenvalues are positive. Okay. And there's also a test, another equivalent condition. So this is like the definition. This is like an equivalent condition. And there's another test, an equivalent characterization of positive definite. All principal minors are positive, or let's say have positive determinants. Okay. So here's an example of a positive, I guess, definite matrix. It's a very simple one. Oops. Right? It's a diagonal matrix. So we see that the eigenvalues are 3 and, well, so first of all, let's check. If you multiply this out, right, so I'm essentially looking at V transpose times S times V. You would get 3x squared plus y squared, which is obviously greater than 0 as long as we're not dealing with the 0 vector. So that's positive definite. The eigenvalues are all positive. And then the principal minors would be, well, the one, so we have the determinant of the 1 by 1 matrix is positive. And then the determinant of the next principal minor, right? So that's determinant of the matrix itself is also positive. Okay, so that would pass that test for a positive definite matrix. Okay. Okay, so here's another example. So here's a quadratic function. Let's call it Q on x, y, and z. So this is a positive definite quadratic form, right? Everything is being squared, there are no negatives there. And the only way this could be 0 is if we're dealing with x, y, and z all being 0. So this is positive for all non-zero points. So this is a positive definite quadratic form, quadric form, whatever it's called. Okay. Now, if we multiply this business out, it's not as obvious. Okay. But we can gather like the x squared terms and the y squared terms, and then the mixed terms. And then you can confirm that you can write this as the vector, column vector with components x, y, and z transposed times the symmetric matrix times the column vector. And what would happen is that in the diagonals, and I think there's at least in Cohen's class, there's some homework where you have to kind of go from this to this. But for the if you have the purely x squared, y squared, z squared term, the coefficients for those are the numbers that would actually go in the diagonal. So yeah, so 10, 1, 1, 2z squared. Oh, that's very good. You're right. And then what would happen is that the mixed term, so you have the xy term. So you have, like, think of it as x and y, I guess. But we can, so this is like the x row, and this is like the y column. But then you would have an xy term here as well, so you can divide this coefficient by 2. And you would get these off-diagonal entries. So likewise for x times z, so x and z, but there's two kind of, x times z is the same as z times x. So you divide this coefficient by 2. And then what goes in the entry that corresponds to the y times z term? Well, yeah, exactly. Okay. So if you have a quadratic form like this, you can always rewrite it in the form some matrix times a symmetric matrix times the vector. Yeah, divide by 2. Oh, for the Hessian, yeah, but I'm not dealing with the Hessian specifically yet, just general quadratic forms. Okay. So then we already know it's positive definite because I actually, I designed the function to be positive definite, obviously, right? Now, we could try to find eigenvalues and confirm they're all positive. Yeah, you always divide by 2 for the off-diagonal entries, right? Because there's only one way to get x squared. It has to be x times x. So there's 10 of those. But like 6 times x times y, well, you actually get 2 mixed terms like this, right? But they're equivalent. Okay. So you would get a 3 and a 3. And you can multiply, you can also do this. Okay, yeah. But so we could find eigenvalues, and we would find that for this positive definite thing, that'll be all positive. We can also use the principal minor test. So the determinant of the top left 1 by 1 matrix is obviously 10. Yeah. So that's positive. The determinant of the next 2 by 2 top left matrix. Uh, 10 times 1 minus 3 times 3. That's still positive. And finally, the determinant of the 3 by 3 matrix itself. So let me, what can I do here? I'll just expand at the bottom row. Times whatever. And okay, so that's going to be 3 plus 0 and then plus 2. Okay. So all those determinants are positive, so it's positive all the way down, right? So it passes the test for a positive definite matrix. So our matrix is positive definite, even though we knew that from design of the quadratic form it corresponded to. Okay. So what then is a negative definite matrix? So that would be where this quadratic form, instead of obviously definitely positive, is going to be definitely negative, right? So S is still symmetric. That's going to be negative for all non-zero vectors. And what are the equivalent conditions? Well, let's look at an obvious negative definite matrix, like so the simplest one being one with one that's diagonal. Right, so if you have X transpose S times X, that would give you, let me just write it out. Negative X squared minus 2y squared minus 3z squared. Okay. So that's clearly going to be not negative. I'm sorry, it's going to be negative for non-zero points. Okay, so that's negative. Okay, so notice that if you, because we're looking at a diagonal matrix S, we see the eigenvalues are simple to find. The eigenvalues would be all negative. So an equivalent statement for a negative definite matrix is that all eigenvalues are negative. Okay. And notice then if I take the determinants of these principal minors, what happens? Well, the first determinant is going to be negative. But the determinant of the next square matrix in the top left is going to be positive because all the eigenvalues are negative, right? So to compute the determinant, you multiply the two negative eigenvalues. So that's positive. And then the determinant of the whole matrix, again, would be negative. Yes. So I'm just motivating a more general test for negative definite matrix, right? So if the determinants here alternate from minus to plus to minus to plus, but starting with a minus, the first determinant of the 1, 1 entry has to be negative. Yeah. So we say that S is negative definite. The final doesn't have to be, the final determinant doesn't have to be negative. So it's possible that a matrix is negative definite, yet the determinant is positive. Just like this matrix, right? It's definitely negative definite, but its determinant overall is positive. It's just that the determinants have to alternate, starting with negative and then positive. If the determinants, I don't know how to write this, I guess I should, M11 is negative, but then the 2 by 2 matrix at the top left is positive, and so on, and they alternate. Right, but then this would be what? This would be positive if n is odd, and negative if n is even. But the idea is that it's alternating signs, starting with a negative. Okay. So, for example, you can easily come up with some silly quadratic form, which is negative definite. Or is it? Well, I have to be careful there, right? Because it's possible that this is 0 even if the vector itself is not 0. So that's a silly example. Okay. That's a silly example. Okay. All right. Well, what's the application of this? Well, so first of all, it has to do with the Taylor expansion, the approximation of the second order polynomial. Oops, did it again. Okay. So it's the second degree polynomial, Taylor polynomial. And if we know that we have a critical point, and this is positive definite, so if A is critical, making this 0, right? And the Hessian is positive definite, so, and we, let's say, drop this term, what happens? Well, the resulting thing must be smaller than what came before. So that means that the function at A is smaller than the function evaluated at points around A in a sufficiently small ball. So this means that f at A is a local minimum. Okay. And on the other hand, if H is negative definite at A, I should say, then we see that this quadratic form would be negative by definition. Remember, H is approaching the 0 vector. It's not 0. So this would be negative. So if you drop that negative term, the result will be bigger than what we had before. So it looks like f of A is going to be bigger than f at some point around A in a sufficiently small ball. So then we say f of A is a local max. Now, of course, it could be neither, right? Like, right, so this is essentially the second derivative test. And like this test would fail if the Hessian is neither negative nor positive definite. For functions of two variables, we would maybe call that if the Hessian has determinant 0, then we don't know what's going on. The test fails. But if the Hessian is neither positive, negative, nor positive definite, negative definite, and its determinant is non-zero, then at least for functions of two variables, we have what we call a saddle surface or saddle point. And your professor did some work, Dr. McCohen, sorry, did some work in proving the second derivative tests using all sorts of inequalities and eigenvalues. Just the interesting part, but. Okay, so let's look at examples of this for a function of two variables. Well, actually, let me do something interesting. So suppose you have okay. If you try to find a Taylor polynomial of this function centered at the origin, say, what do you think you're going to get? So what do you think you're going to get if you try to find a Taylor polynomial? Okay, well, let's see. So let's evaluate the function. Near 0, we're going to have, and it's not whether we have a saddle point or not, but just if you do a Taylor expansion for this, right, we would want to, there's the Hessian, so possibly plus some more stuff. So what is the function at 0, 0? Well, it's equal to 1. Okay, oops. And what is the derivative of the function at 0, 0? Well, it's the matrix of partial derivatives, the derivative with respect to x, and then partial of f with respect to y. Okay, so that's this derivative, and that's going to be evaluated at the origin times xy. Okay, so let me just update that. So at 0, 0, this will be 3 minus 1 times xy. Okay, and then we have 1/2 xy, and now we have the second order derivative. So let's say fxx is 2. I'm going to write it over here. Fyy is 2 as well. Xy is -7, and so is fyx. Okay. And now, what are the higher order derivatives? Like if you had the third order derivatives, they would all be 0, right? Because the second order derivatives are constant. So if you keep differentiating, you just have 0. So nothing else is left there. Okay, so that's actually it. And we can multiply this. And let's see, this would be 2x squared plus 2y squared. And then negative, so -7, -7, it's -14 x times y. Okay, so doing a Taylor expansion at the origin, we get this function, this polynomial. And how does that compare to the original? Right? It's exactly the same thing. So why would that be? Right. Well, this function is already a second degree polynomial in x and y, so you'd expect the Taylor expansion to also be a second order polynomial. So it's exactly the same thing. Okay. So that was a fun example for me. But now let's go ahead and look at an optimization problem. So we're going to find local extrema for a function of two variables, a real valued function on two variables. Okay, and we're going to classify the critical points by using the second derivative test. Okay. Seven halves. I think it's 7 if you're referring to this, because we had a negative 14, but remember there's a 1/2. Yeah. Okay, so let's find critical points. So we know that if we have a critical point, the derivative has to be 0. So we compute the derivative. So partial f with respect to x and then partial of f with respect to y. And that has to be 0. All right, so if you'd like, we just take all the partial derivatives and set them equal to 0 and solve the system, right? Solve for critical points. Okay, so that should be easy enough in this problem. Partial of f with respect to x should be 0. Partial of f with respect to y should be 0. So the first equation tells us that x and y are equal. So then we go to the second equation and use this fact that x and y must be equal. We factor here, I guess. And then we find three values of x, right? So x and y. So the critical points. So x could be 0, in which case it has to be 0. X could be 1, and x could be -1. Okay. I guess we'll come back to this little table. So we found three critical points. Now we're going to classify what happens at the critical points by using the second derivative. Okay. So we're going to create the Hessian matrix. And evaluate at the critical points, right? So fxx is it's 4. FYY is FXY is -4. So FYX should also be -4. We can confirm that's true. Okay. So the Hessian here is, oops. Okay. So we can take each critical point, let's say 0, 0, and evaluate the Hessian there. Okay. So is this Hessian going to be positive definite, negative definite? Neither. So we can just use our test. The determinant of the 1 by 1 matrix at the top left is 4. Positive definite for sure. Okay. And the determinant of the full matrix is positive. Oh, hold on. It's neither, right? Because we get 0 minus a -4 times -4. So it doesn't pass the positive definite test. It doesn't pass the negative definite because remember we would have to have negative positive. So it's neither, so we can say that we have a saddle. Okay. So we have a saddle. So there's a saddle at the origin. Okay. Okay. So we move on to the next critical point. So let's say at 1, 1. The Hessian at 1, 1. 4 minus 4, -4, 12. So now it's positive definite. You get a 4, and then the determinant of the Hessian itself, (48 minus 16). That's positive. So this is positive definite. And so what can we conclude about what's going on at this critical point? We can say that F at 1, 1 is a local minimum. Yeah. And I think the same thing would happen at -1, -1, right? The Hessian would still be positive definite. It's the same matrix. Y is being squared, so it's positive definite. All right. So we have again F. So for the so you can say the function attains a local minimum at the point -1, 1. Okay. What else can we talk about here? I mean, I have many optimization examples with 3 variables as well. Ouch. Okay. Yes, so the Hessian being positive definite at a critical point means local minimum. And the Hessian being negative definite at a critical point. So remember, the first derivative has to be 0. Yes, it's a local max. That's right. And for a function of two variables, at least, if the Hessian is neither positive nor negative definite, but is determined as non-zero, then we have a saddle. Right? It's also possible that the Hessian has determinant 0, so that second derivative test would fail. Okay. Yeah, it's different. So I'm going to try to get actually 2 reviews, like one after the other, one for Dr. M, one for Dr. K, because I don't know where these 2 professors are going with this. So, do y'all have any questions? Did I? So, like, if we were asked for the Hessian for an n by n, yeah, so we can easily come up with a Hessian for an n by n, say 3 by 3. You just kind of create a function. But differentiate it, right? So how would you find the Hessian for this matrix? Well, you would need all the second order derivatives. So there's, how many of those are we going to have? Well, there's 3 variables. We're going to get a 9. Yeah. So we're going to have to find the partial of f with respect to x twice, and so on. So this can become really tedious, I guess. I would first find all the first order derivatives. Oops, getting ahead. And then you would find the second order derivative. So I guess fxx. So differentiate this with respect to x. Okay, then fxy. So differentiate that with respect to y. And fx and then z. So differentiate that with respect to z. Then partial of f, so fy x, differentiate that with respect to x. I mean, this class kind of becomes boring when it becomes an exercise in taking partial derivatives. Then fyy, so differentiate that with respect to y. And then fyz, so differentiate that with respect to z. How do we have in Prof K, we get partial derivative matrix can be expressed with the variable n? I don't know why I'm assuming that. Yeah, so like for Dr. K's like n by n matrices, using the test for positive and negative definite matrices, I guess he can use induction, or maybe use the fact that a real symmetric matrix has a orthogonal diagonalization. So he hasn't gotten there yet. So we'll see how Dr. K approaches that. But he can prove it. You hope he doesn't. Oh, he will. I'm sure he must, right? Well, would you rather work with optimization for functions of matrices or something? Okay, so FZX would be FZY and Z. Yeah, but I wonder, yeah. I forget how to prove that test. I forget if it was by induction or if it was using eigenvalues. So if you have a real symmetric matrix, remember that there exists an orthonormal basis. So this is from linear algebra. There exists an orthonormal basis. So that's n by n. You think, yeah, I think induction might work. For Rn. Orthonormal basis consisting of eigenvectors for matrix S. So in other words, you can create a nice basis for Rn just using eigenvectors of the matrix S. In which case, if you have your eigenvectors, let's say P1 through Pn that are orthonormal, then this would give you S times P1 would give you the first eigenvalue times P1 and so on. I'm trying to recall Pn. Right, so that would give you the nth eigenvalue. And so you can write this, you kind of create a matrix P whose columns are your orthonormal basis of eigenvectors. And this can be written as a diagonal matrix where the diagonal entries are your eigenvalues times the matrix P. So then S is equal to, it's an orthonormal matrix, so it's just, you'd multiply, oops, the other way around, yeah, my bad. So then because, right, P transpose times P would be the identity, because the eigenvectors are mutually perpendicular. Say, let's just look at two of these. And they're orthonormal, so they have unit length. Oops. So when you multiply P transpose with P, you get P1 dot P1, which is 1 because of the unit length. P1 dot P2 is 0 because they're orthonormal, and so you can prove that's the identity. So in that case, P transpose is the inverse of P, so you can multiply both sides by P transpose. And you get a symmetric diagonalization. So let's see. So then if you have x times x times x, you can replace s with this diagonalization here. And you think of this as P transpose times x, but transposed times the diagonal matrix. Okay. And so you just define some vector u to be p transpose x, and then you have a very simple quadratic form here. Because remember that the diagonal matrix just has the eigenvalues. And when you, since you only have the diagonal entries here, this becomes mu1 times u1 times u1 and so on. And you all recognize this as being right. So one of these eigenvalues is going to be maximum. Well, so if you assume that all the eigenvalues are positive, right, and you look at the maximum one, then this is going to be at most, or you take the minimum one. Yeah, the minimum one, just positive, and then you have magnitude of u squared. So this kind of proves that if all the eigenvalues are positive, then if u is non-zero vector, right, then this will be positive as well. And since that's positive, yeah, okay. So it'll be, so if all the eigenvalues are positive, then your matrix is definitely positive definite. Now, how do you extend that to the test? Should I use, would you use induction or no? And I guess you also would want to relate this u to, so how do you relate the magnitude of u squared to the magnitude of x? So this is identity. They have the same magnitude. Interesting. Okay. So this is even better. Okay. So this is actually pretty important proof of the fact it's used in McCohen's class to prove the second derivative test, that if you have v as v and s is positive definite, then this is greater than or equal to some number. So here I found it explicitly as like the minimum. That's some number that works here is the minimum eigenvalue, but some number n times the magnitude of v squared. Okay, where m is positive. Anyway, I thought that would lead me to an idea for the proof of the test for positive definite, but sorry. Anyway, unless you have more questions. I really wasn't sure what to cover here because I was really worried that, I don't know what's going to be on the exam for Dr. K. I would recommend going over the homework. I wouldn't expect things to be too radically different. So your limits, finding funky determinants, interesting determinants. What else is there? Limits, spherical and cylindrical coordinates. Yeah. taking derivatives, the formula for the derivative of a multilinear map. Maybe some proofs using the definition of derivative, either, right, we like the directional derivative definition, so Guiteau and then Frechet. $66 out of 120. What was the median? Do you know? Ouch. Let's close. Yeah. Was it difficult? 266. Okay. Yes, he said 8 out of 10. Yeah. It's pretty bad. I wish I could see the test. I hope Dr. K releases a PDF of the exam. Anyway, thank you, everybody. Right, later.